Good afternoon, everyone who's joining us here on Geo. This is our first lecture of the term today, and we're joined by Dr. Chris Spencer from the University of West England in Bristol. And he will be talking us today about coastal landscape development. He's a lecturer in physical geography at the university, and his research centres around reconstructing past changes on coastlines in recent geological periods, changes in sea level, and the impacts of storms and tsunamis. So without further ado, I will leave it over to you, Chris.
Thank you very much. And thank you for either sort of attending live or clicking on this to sort of watch it at a later date. The plan for what I'm going to try and talk about, and what I am going to talk about, is coastal landform development. And I'm going to explore that through a location, Sand Bay on the Somerset coast. And as part of that, what I'm going to try and do is to look in the first instance at introducing the site and some of the key coastal processes. So what are the main drivers behind change and the key energy sources affecting this coastline? And then in particular, what I look at is why we have such a variation of coastal landforms at this site. Now, that's partly to explore what is it that gives us a particular coastal landform at any one point. And to get to a point where we can look at how each of these landforms is there as a result of a really kind of delicate balance of different factors, and that small changes in any of those factors, whether that's the geology or the sediment supply or the wave energy, any small changes in any of those elements that influence our coastal landforms can result in quite a different coastal geomorphology, different coastal landforms. And the reason why I'm kind of trying to work towards that point and sort of explore that through a range of different coastal landforms at this site is that towards the end, I want to then think about, so what does that mean going forward? What does that mean for the future of coasts, and potentially even what does that mean for the future of how we will use coastlines and hopefully sustainably going forward. So that's what I'm going to try and work towards. As I say, the first part will go through this sort of exploration of a variety of landforms at this particular site. So where we're looking at here is in the Severn Estuary, underneath this sort of red pin here, just north of Weston-super-Mare, within the Severn Estuary in southwest Britain. And as with any sort of coastal investigation, coastal sort of topic, I think the first thing to think about is coastal processes. I think as coastal geographers, almost straight away we should start asking ourselves certain questions about what are the waves like here? Is it a high energy wave environment? What's the prevailing sort of wind and wave direction? What are the tides like? What sort of scale tides do we have? What's the local geology? Maybe looking at what is the predominant sediment types here? Where does the sediment come from? So we're going to be exploring this site, as I say, just north of Weston-super-Mare within the wider Severn Estuary. So to look at it in a little bit more detail, so this urban area towards the south of this digimap image here is the sort of northern edge of Weston-super-Mare, and Sand Bay is this relatively wide sort of open bay immediately north of Weston-super-Mare. And towards the north of that bay, we then have this headland that protrudes out into the Severn Estuary. And we're going to be looking at the landforms either side of this headland. So a really quite a small area, maybe 2 or 3 kilometers square, sort of in this sort of area. And we've got quite a lot of variation that we can maybe even pick out from the level of this aerial image, that we've perhaps got shore platforms here on the northern edge. We've got a range of different bays here. We have this sort of green area of the salt marsh. I've labelled in here some sand dunes, not so obvious from the image, but we've got some sand dunes down here, all packed into a really, really small area. And so I think there's quite a bit of work to do here to explain why we would have all of these different coastal landforms in this really small area. But first of all, to think about some of the coastal processes. So in this area, Avonmouth is just a little bit further into the Severn estuary, but what I've got here is the windrows for this area, and very strongly the winds here are coming from between the west and the south, so predominantly from the sort of southwest are our strongest winds. That's where our sort of biggest waves are coming from that would approach this coastline, and waves as they progress towards this coast maintain their power initially as they move up the estuary, moving quite powerfully, but as you will know from your studies on waves, that as they move into shallow water, the seabed starts to interact with the waves, and the wave starts to break, and they start to lose their energy. Their energy is sort of dissipated as they start to break. So we're on a pretty exposed coastline here. We're exposed to the widest Severn estuary. We're exposed to the sort of Atlantic Ocean, and big, powerful storms can track up the estuary and reach the site. We haven't had one for quite some time, but yeah, they can be pretty powerful and rather damaging when they do happen. So it's a relatively high energy coast from the point of view of wave power. And then tides. Severn estuary renowned as having very high tidal range, that vertical difference between high and low water. So this image here essentially sort of demonstrates on the legs of one of the Severn crossings the difference between high water in the image on the left and low water in the image on the right. And the vertical difference between the two is around about 13 meters. And that's huge from the point of view of tidal ranges. That's enormous. It's globally significant. So if we were to look at the distribution of tidal ranges around the globe, the black shading are areas with a tidal range of more than 6 meters. So there's not that many areas of the world with a tidal range more than 6 meters, and we're at 13 meters. So we're right at the very extreme end of that certainly in the Severn estuary and southwest Britain more generally. Only other place with a higher tidal range is the Bay of Fundy over here in Canada, that in places has a tidal range of near 20 meters. But you know, it's a very extreme, very powerful tides along this section of the coast. And I've just got a few images here that we're going to come back and look at each of these sets of coastal landforms and try to start to explain the variation that we have and understand how we end up with different types of landforms. So we have different bay morphologies, different bay shapes here. So on the northern edge of the headland, we have Swallow Cliff, this sort of very narrow kind of slot cut into the rocks that exists on the northern edge of this headland. And yet elsewhere, just further along the same headland, maybe 700-800 meters further along, we have this much wider, much more open bay, which has been cut into the same headland. So really quite different characteristics, not too far apart. We need to sort of explore and be able to explain why that would be the case. We'll come back to that in a second. And we can look at the cliffs. So either side of this headland, maybe only 200 meters apart, 150 meters apart maybe. On the northern side of the headland, we have these vertical, near vertical cliffs. And yet on the southern side of the headland, we've got these much more shallow sloping cliffs. Very different coastal geomorphology, very, very close by. And a characteristic that all of the northern side of the headland has near vertical cliffs. All of the southern side of this headland has much more shallow sloping cliffs. There's got to be something controlling that. We can look at what the drivers are behind that difference. We've then got the beaches themselves. So to the north here, we have a number of sort of gravel beaches. This one in particular, in this sort of more open bay at Middle Hope. So we could look at perhaps how beach energy is different. Steep slopes on these gravel beaches made of different sediments or gravels rather than sands. Whereas to the south, we've got much wider, flatter sandier beaches. Again, there's going to be controls behind that, and what's influencing things like beach slope, why the beach is steeper on the gravels and more shallow on the sands. And how could we investigate that? I'm going to introduce some bits of data that my students at UE Bristol and also some students from a local college we work with have collected at this site to sort of test these theories. And then sort of finally, for these different landforms and the variation, part of this large bay of Sand Bay has a very significant salt marsh, maybe 700-800 meters north to south, 400-500 meters east to west. So it's this significant landform, and the salt marshes might conjure up ideas of very low energy, muddy sediments, tide processes kind of dominating. And right next to them, we have sand dunes. This is the photo from exactly the same bay. We have these sand dunes here with a small sort of sandy beach in front of them. So two landforms that don't necessarily feel like they should sit together so closely. So again, we need to explore why that might be. How are they sort of coexisting so close by? So as a first thought, we might sort of think, so what factors are driving this variation? What are the key processes that could be giving us such differences? And I think a good place often to start, probably the most important energy source that we have at the coast is wave energy. But then why would that vary over such a small area? Why in this very small zone would we get such a significant difference in wave energy such that we can get salt marshes and mudflats existing very, very close to sort of eroding limestone cliffs? And what we can do is we can look at what might influence wave energy. That when we look at the bathymetry, the depth of the water around this coastline, we can start to see that the wide open bay, and this is just a sort of basic GIS that I've pulled together here, this wide open bay here has very, very shallow water. The oranges and the sort of beige colors are very, very shallow water. And so if we think back to our sort of wave processes knowledge, as waves approach this shoreline, as they move into this sort of wide open bay, they start to lose their energy. They start to break. Their energy is dissipated. Another part of the same wave that's tracking towards this coast, but that moves into the more northern part of the site, north of the headland, doesn't experience the same shallow water. We have very little of the oranges and beige sort of colors here. So those were the same wave with the same amount of sort of potential energy tracking towards the north here, stays in deep water, keeps traveling quite quickly, maintains its energy, and then breaks onto the shore. So that could be a starting point to explain why we have such difference. That north of the headland, we have deep water, and we might then infer more powerful waves. South of the headland, we've got much more shallow water, and we might infer there that the waves are losing their power to be dissipated across the bay. Okay, so by using that, if we've now got higher energy on the northern side of the headland, we could start to look at some of these bays to think, so why are they the way they are? Why this very narrow sort of slot cut into the rock here at Swallow Cliff Bay, and this much wider beach a bit further along? So if we're thinking about cliff erosion, and we think about all of those processes of quarrying and abrasion and attrition of the rocks in front of the cliffs, we think, okay, so what might influence those? Well, wave energy might be a place to start, but we've already looked at that, and the wave power should be broadly similar across this northern edge. Another thing we might think about is rock type, and that's quite important when we think about how cliffs behave and how susceptible rocks are to being eroded. And when we look at this coast, we can actually see we've got quite a number of bays. We've got this very narrow, long sort of slot cut in over towards the west here. Then there's our more open bay at Middle Hope, another little narrow bay here, and another little narrow one a little bit further to the east. And when we look at the the geology map here, I'm going to sort of toggle between these a couple of times, we see that tracking underneath this narrow slot bay at Swallow Cliff over in the east, we have this rock represented in pink on the geological map. And then when we've tracked that through here, it occurs again in our wider, more open bay at Middle Hope. And then because of this fault, this solid black line here, it's sort of offset. And again, our rock represented in pink is exposed again here, perhaps giving us another one of those narrow bays. So if I toggle back, the rock represented in pink is kind of under here, underneath this wide bay, is then underneath this much wider sort of open bay, and then again under this little narrow bay here. So maybe the rock type is part of the story. So we can then investigate, okay, what's that rock type though? So this rock is volcanic tuff. Now, unlike the name suggests, volcanic tuff isn't particularly tough. It's a volcanic ash deposit, which is, in this case, was laid down onto the ocean, settled down to the seabed, and then eventually sort of solidified. But it's not a very resistant rock. The sort of bluey grey on this map is limestone, a much more resistant rock. And we could look at some data that my students have collected from this site as part of a project, a little bit like the NEA that some of you will be working on at the moment. And what they've done is that they've looked at rock strength at this site, and there's a couple of different types of limestone here, and this box and whisker plot sort of shows that the limestone, either the pure limestone or the limestone mixed with the volcanic tuff, are both pretty resistant. They have a high rock strength, and so they're quite resistant to erosion by the waves. Whereas the volcanic tuff in particular is very low rock strength, much more susceptible to erosion by the waves. There's also a small outcrop of basalt here, which is also relatively weak, and it appears with these volcanic tuff. So this that could be a good hypothesis that this is what's controlling the formation of these bays. If we start to look at this geological map again, it may look a little bit more similar to some of the images you may well have used in your studies and in your textbooks. That if we look at how the rock outcrops, how it's exposed here at Swallow Cliff, it meets the coast at right angles, and the waves erode along that bed of volcanic tuff. So it's a discordant coast. The rocks are meeting the coast at right angles. The same rock type is here. This sort of pink rock at Middle Hope is exposed sort of parallel to the coast over towards Middle Hope. And so it's much more of a concordant coast, giving us a wider, more open bay. And then when the same rock is exposed further here, it meets the coast at right angles, giving us a more discordant coast. So rock orientation is key here. The rock type doesn't particularly change, but that one small variable and the angle at which the rocks meet the coast results in very different bays being developing here. So the coast it's very responsive to small changes in the coastal characteristics. Okay, so one of the other characteristics that I briefly introduced earlier was cliff morphology. So here on the northern side, again towards Swallow Cliff, we had these near vertical cliffs, whereas to the south we had these much more gradually sloping cliffs. So we need to think about what might be driving that sort of difference. And if we start to list the various things that could be influencing that, it could be rock type. Maybe one rock is much more resistant and the other one much less so, more likely to collapse, thinking of all of the different ways that we get mass movement at the coast. Maybe it's the same rock type, but we have different amounts of jointing, more planes of weakness on one side, giving us a more gradual slope, less planes of weakness, less erosion on the other side, giving us a more vertical cliff. Differences in rock strength, differences in the bedding of the rocks. Are they laid horizontally, or are they dipping, the rocks dipping down at a particular angle? Maybe differences in wave energy, and so on. So similar kind of thing. We've done research on this coastline, my students looking at projects on this coastline have carried out this work. They've, using very simple pieces of equipment, clinometers that you may well have used in the field yourself, have investigated the differences in the angle of the cliffs, distinctly steeper on the northern side, 70 or 80 degrees, distinctly more shallow on the southern side. So we've statistically demonstrated we have a difference. And then they've looked at jointing, the box plots plot pretty much next to each other. No difference in jointing. Rock strength doesn't vary. It's all limestone, so the rock type doesn't vary. And when we look at the bedding, that doesn't vary either. So it's feeling like we've maybe missed something here. But when we explore this through, I'll explain to you how the rock bedding is hugely influential, even though it doesn't vary between the two sites. So what's going on here is that we've got either side of the same headland, but on the northern side, those rocks dip towards the land. That gives us a very stable cliff because the rocks are trying to slide inland along those planes of weakness along the beds. On the south side, the rocks are dipping towards the sea, the other side of the same headland. And we can see the bedding in this photo here with the rocks dipping at around about 30 to 40 degrees to the south. I flipped this image round so that it mirrors the cliff line that I'm showing underneath. That's why the odd text, I've just flipped it in PowerPoint. But that's a much more unstable cliff line. And so when we get erosion at the base of this cliff, eventually the beds, perhaps this large bed that we can see here, if we were to get erosion at the foot of that bed, that rock would all slide off and into the sea. So it can't support anything like as steeper cliff as the rocks on the other side. So it demonstrates the importance of rock bedding. Cartoons here that sort of show the same. I couldn't flip the video in Cliff Structure 3 because it wouldn't let me flip the cartoon, but Cliff 4 shows us how their rocks dipping towards the land are very resistant. So it takes a lot of erosion here, a lot of abrasion and quarrying at the base of this cliff to develop a wave cut notch before eventually we might get a collapse. But it can support a vertical cliff. On the image here on the southern side, as soon as the waves start to nibble away at the base of the cliff there, the abrasion and quarrying takes the material out, the beds will slide off and into the sea and then sort of gradually get broken down by waves. So again, only a relatively small sort of difference here gives us very different coastal outcomes, quite different coastal landforms. Now, it's important that we think about that and then how these sort of cliffs and the erosion, the bay formation and so on is controlled by these very small changes in geological characteristics. And that these cliffs and these landforms have evolved over very long timescales. Cliff erosion is really slow, in the order of maybe millimeters to sort of centimeter, centimeter in a really sort of high energy year, millimeters in sort of normal years. But in geomorphology, we have loads of time. So even though we've got very slow erosion, adding that up over many, many thousands of years, it can start to explain the cliff erosion that we see. And these coastal cliffs that we're looking at this site will have been active since sea level stabilized approximately 6,000 years ago, something of that kind of order. And we can start to think, well, is that long enough to explain all of this erosion, all of the erosion that we've got on these cliffs and opening up all of those different bays? Is 6,000 years enough at these very, very slow rates? I think it's worth considering what else might be going on here if it's not 6,000 years. And to do that, we need to scale up a bit in terms of time. So throughout the Quaternary period, our current geological period, it's characterized by climate change, shifts in climate from glacial periods when ice spreads out from the poles, such as the cartoon here showing ice spreading out across North America, same kind of thing going on in Scandinavia, Europe, Central Europe, into Russia and so on. So we've had periods of glacial interspersed with periods of interglacial, like the period that we're in now. And that these are relatively regular, predictable switches between the two states, driven by variations in the Earth's orbit, these Milankovitch cycles. I know some of the A-level syllabuses cover this to a little bit more depth than others, but essentially variations in our orbit around the sun, whether that's what we call the eccentricity, so is that our orbit being more circular or slightly more elliptical, or whether it's the tilt of the Earth towards or away from the sun, the angle of that tilt, or the sort of precession of the equinoxes. So are we close to the sun during our winter or our summer periods, influence the amount of solar radiation we receive. And that, if we had a period of low solar radiation, we have a glaciation. Higher solar radiation, we head in towards an interglacial. Okay, so, and then if we think about where we are today, so here's our climate change story through the last 2.6 million years. And we're right here. This is the present day. We're at the end of this kind of red line with relatively warm conditions, and as a result of that, relatively high sea levels. The ice has melted back. We have ice still in Greenland, Antarctica, the Alps, the Andes, and so on, but relatively little ice compared to a glacier. And we've had this tiny little bit of time where our cliffs might have been active. But if we think about it, if we look at the story over the last 2.5 or so million years, sea level will have been roughly where we are now over and over again through this time period. So those cliffs have not only been active for 6,000 years, they'll have been active every time sea level was roughly where it is now. So that gives us loads more time for all of that erosion to have happened, all of those bays to have opened up over successive periods of high sea level each time we had an interglacial. And then we've got the troughs. So the troughs are when we've had globally we've had a glacial. It's been cold, and we've had many glacials. Each of the troughs on this graph, the low points, are a different sort of glacial period. So we could think about how has this site looked over these cycles. So at the height of an interglacial, it looked roughly like it does today. This is about sort of mid-tide here. So at high tide, the waves will be working on these limestone cliffs, progressively sort of eroding them away through time. In some of our interglacials, it's been warmer, and the height of the tides would have been, the height of the sea would be even higher, others perhaps a little lower. So it would look roughly as it is today over and over again during different interglacial periods. But then during our glaciation, stuff didn't stop. I mean, where we are here on the southern side of the Severn Estuary, we weren't glaciated, but it would have been cold. It would have been really cold. We would have had periglacial conditions. And during that period too, there would have been erosion of these rocks. There would have been all sorts of periglacial processes, frost shattering and so on, all acting on these rocks. So their story is much longer than that sort of 6,000 year period of our present day sea level. So time is there. Processes change through time. Processes change with changes in climate. Processes change with changes in sea level. So if we then scroll back to, okay, what was the story since the end of the last glaciation? So 18,000 years ago, the ice was at its maximum. A bit further north of where our site is here, we weren't glaciated. We were periglacial. We were close to the glacial. Sea level 120 meters vertically lower. So the nearest coast to where we are now would be where we're dealing with in this lecture, would have been a way off here in sort of southern Ireland, sort of, south of Ireland. And then the ice starts to melt. By 15,000 years ago, there's patches of ice here across the Lake District, southern Scotland, and into Northern Ireland, maybe a few patches in Wales still. And then over the last sort of 10,000 years, sea level gradually rose, and the map as we see it today starts to emerge. And that's when we're getting our cliffs are active again during this interglacial period. But also all of those other coastal landforms become active, our beaches, our dunes, our salt marshes. So if we look at then some of those other sediments, the beaches and dunes, and see how we have variation there too. Well, energy was different north of the headland where we have the deeper water, the waves being more maintaining their power, we tend to have these gravels, whereas to the south, we have sands. And the gravels tend to have steeper slopes. We need to sort of think about what process is driving that. Why do we have different slopes on different types of different beaches? So on the northern side, we have higher wave energy. We've got erosion of those limestone cliffs, and the gravel starts to build up in the bays. Whereas to the south of the headland, we've got the shallow water. Waves lose their energy as they're moving into the bays, and so we don't have gravel transported. The waves don't have the power to transport gravel in there. We get sands, we get silts and clays and mud. And that results in quite different beach characteristics, the gravel beaches being much steeper than the sand beaches. And that all comes down to a fairly simple relationship. Probably one of the first things that you studied at school in terms of coastal processes are swash and backwash. And I think probably when I was a student, I was probably quite quickly fairly dismissive of them, being almost insignificant. Why am I learning about this? I've been on a beach, I've seen a wave come in, I've seen a wave go out. What does it do? But they're actually really important, and the relationship between the two can tell us a lot about how our beaches form. So if we think about a gravel beach, so we have our swash, the wave breaking and running up the beach. We have our backwash, the wave moving back down with gravity back out into the sea. And on a gravel beach, when waves break, the swash runs up the beach. You may have been on a gravel beach and seen exactly this happen. It makes a fantastic noise as the waves kind of foam and run up the beach. But then the backwash tends to sink into the gravel. We don't really see much evidence of the backwash. It seeps into the gravel. It's a very lots of gaps. It's very porous, and the seawater can seep into the gravel, and the backwash returns through the beach. And as a result of that, we have a relatively powerful swash, but a relatively weak backwash. And so material is continually thrown up the beach. The gravels are transported up the beach, building the beach up sort of higher and higher gradually sort of through time. And so on gravel beaches, they tend to be quite steep because of the backwash seeping through the gravel. Whereas on sand beaches, the swash and the backwash are much more equal. That the swash runs up and over the sands, very little percolates through, and so the backwash runs across the sand back out to sea. So they're much more even. We don't get so much dominance of one over the other, and we don't get as much material transported up the beach. Our beaches tend to be, sand beaches tend to be much flatter. And again, we can test this with some really simple measures. We can look at things here. So we've done this with a college local to us in Weston-super-Mare, where students have looked at measuring beach angle. So on the northern side of the headland, we're demonstrating that typically beach angle is steeper than to the south of the headland on the sands. We're somewhere around 10, 11, 12 degree slopes on the northern side, much smaller slopes, around perhaps 4-degree slopes on the sandy beaches. That we can then look at what are those beaches made up of. We use calipers to measure the gravels, or grain size cards to measure the sands. We have a range of gravel sizes, but coming out somewhere in the region of maybe mean sort of grain size of 60, 70, 80 millimeters. Sands much smaller. And so we've demonstrated there's a difference in particle size. And then if we look at the rate of percolation by putting in a tube and pouring in 500 mils of water and timing how long it takes, we can see that on the gravels, it's almost instantaneous. The percolation is much faster than it is on the sands. Really simple measures to sort of test that theory, test that concept of is this relationship of angle, particle size, and percolation, does it sort of stack up? And it appears that it does. That on the northern side, we have gravel beaches that are steeper because of this rapid percolation, and to the south, we have the opposite. So again, one factor is changed here, the particle size, and we get a different morphology of our beaches. Okay, and then the final element of variation I want to sort of quickly introduce here are how we've got these very different landforms of salt marshes coexisting right next to sand dunes. And these systems aren't static. They sort of change through time. And again, I've produced another GIS, using a GIS-based map here where I've plotted the coastline in green here from the 1900s. The 1900s survey is the green line here that shows the high water mark in the 1900s was all the way back here. And so our salt marsh that exists in this corner in the present day didn't exist then. We had this green line was the high tide line. And at the back of the beach here, there are old sand dunes. But then by the 1970s, this slightly more kind of purple line, it may not be easy to pick out on the screen, but the purple line here, the high water mark had moved all this way offshore. That salt marsh had built up. This salt marsh that's perhaps, as I said before, 600-700 meters north to south, 400-500 meters east to west. A huge landform had been built up over the sort of 70 years between those two surveys. And that salt marsh had sort of gradually started to bury and cover the old sand dunes. But when you think, well, what would be driving that change? So looking into this is where we might be sort of thinking about the kind of NEAs that you're doing. We were looking at what's driven that and using the literature, using what's written about this coastline. And we came across evidence of some large-scale changes within the Severn Estuary. And this author here, Bob Kirby, had done a series of boreholes offshore from this area and had identified that within the Severn Estuary, there was very little sand left. So whilst there had been beaches and sand dunes present on this beach, there was no longer really that much sand to feed the beaches and to feed the dunes. What there was lots of silts and clays, the sort of muddy sediments. And this piece of research here showed how the proportion of the more muddy sediments had gradually increased through time. So that's part of the story, is that there's an abundance of mud within the estuary, but not much sand to build the beaches and the dunes, keep feeding them. But I think we've also got a positive feedback active here, that within this wide bay, we're having sediments are being brought in and deposited. It's a depositional environment. And that as this beach builds up with sediment, the beach height gets higher. And as a result of that, the water gets a little shallower. So waves lose more of their energy. Because the waves lose their energy, they deposit even more sediment. So the beach builds up, the water gets shallower, and so on. So we have sort of a positive feedback of more and more deposition, reducing wave energy more and more sediment being deposited. And because the energy is less, it's more and more of the fine-grained sediment is being deposited in this bay. And eventually a threshold is passed, that it builds up more and more and to a point where perhaps it's built up so high that some of the areas right at the back of the beach here were exposed at high tide, maybe for long enough just so that the first plants could start to colonize, the first salt marsh plants the pioneer species that could start to colonize that area. And then that speeds up the positive feedback even more, because those plants create friction, we get even more deposition, and the salt marsh starts to spread and capture more and more sediment growing out, as I say, to create this quite significant landform over a really short time scale. 70 years, this large salt marsh has developed. And we can see there that it's now made up of these very muddy sediment. Students here doing some vegetation survey work on the front of the present day salt marsh. But that very same positive feedback of more and more deposition, water getting shallower, waves losing their energy, more deposition of fine-grained sediments has had another impact. That positive feedback has resulted in, elsewhere in the bay, are sand dunes, which had existed there for some considerable time. It's quite a wide area of sand dunes, many meters wide. But sand dunes rely on as having a wide, dry, sandy beach. And then the onshore winds blow across that beach, transporting sediments to the dunes. Now, our beach isn't dry anymore. It's not so sandy. It's much more of a wet, muddy beach, and you can sort of almost see that in the background of this image, that it's quite a saturated sort of wet beach in the distance. So there's relatively little sand being fed up the beach. The key process that would feed the dunes is saltation, the bouncing of sand across the beach by being transported by the wind to feed those dunes. But that's not really happening anymore. And so the dunes are starved of sediment. They're becoming overstabilized. And non-dune species are starting to colonize these dunes because they've not got the constant burial of new sand being blown in. And so they're becoming something of a relic. They exist still, they're still there, they exist right next to this salt marsh, but they're no longer perhaps the landform that makes sense under current conditions. So it's something of a relic landform next to the salt marsh, which perhaps does better represent the present day conditions. So only, we've got a real delicate balance here of coastal processes and influences. And the point of going through all of that, looking at the variation that we've got, is to hopefully get a feel for how the coastal landforms exist in this fairly delicate balance. And change one thing, we get a response from the landforms in some form. So a really good example of that is the way a beach responds to a storm. Again, here I've got some data based on our first year field trip. We get our students to survey across the sand dunes and onto across the beach. And very helpfully for my study, but not so helpfully for the coast, there was a whacking great storm happened between the 2 days when we visit the site. We go with half of the group one day, 2 days later we go with the other half of the group. So on the Tuesday, the first visit, a group of students plotted up the blue line. They looked at the beach pre-storm, and it produces this blue line when they plotted up their data. Then the big storm hits, and then the other half of the group goes out on the Thursday, and we were able to plot up the same profiles, but it gave us a very different shape. And in all cases, what happened was that we were seeing erosion of the upper part of the beach and the front of the dunes, and deposition on the lower part of the beach. That pattern recurs across each of these beach profiles. So the beach has changed shape in response to the storm. We can sort of see this. So here's me stood next to one of the groins on this beach. We can see a burnt bit on the groin there, and there's the same groin 2 days later. So it was by my ankles 2 days before. It's now sort of, I don't know, chest level. So there's a significant amount of the upper beach has been eroded away there. If we think about what's driving that, that's again, it comes down to the relationship between swash and backwash. This during the storm, waves arrive closer together. So wave breaks. We have the swash runs up the beach. Backwash starts to come back down the beach, but crashes into the next swash. So each swash is weakened because it crashes into the last wave on its way out. Swash gets weaker. Backwash stays about the same. All that water still has to get off the beach. So we have destructive waves because of the relationship between swash and backwash. Backwash now being more powerful. And so sediment is washed down the beach and deposited further offshore. And then we go into a calm period and we hope that swash starts to dominate again and push that sand back up the beach. Now our beaches are very responsive and respond to changes in energy, particle size, geology and so on. So we've got this very delicate balance, easily upset. Naturally we get change. But our coastal landforms respond to these fairly small changes. Now, we know that we're heading into a period of quite significant change. And this links very nicely, I hope, into the geography syllabus, that we know of large-scale changes in the carbon cycle, that we've been speeding up one part of the carbon cycle in accessing ancient carbon, bringing it up in the form of coals and oils and gases, bringing it to the surface and burning it for power or heating or for transport, and releasing that carbon into the atmosphere. At the same time, we've weakened another part of the carbon cycle. With deforestation and so on, we've weakened the process that takes carbon out of the atmosphere. And then all sorts of other elements like intensive agriculture increasing sort of methane emissions and so on. So we've disrupted the carbon cycle, and the net result is more carbon in the atmosphere. And that we know that traps more heat, more outgoing radiation is then trapped. And if we start to warm the globe up, that starts to disrupt the water cycle. And as a result of that, temperature is one of the major controls on how water behaves. And so heating the globe up causes the ice to melt more quickly and moves where water is stored. It's no longer stored in the cryosphere, in the ice, in its solid state. It's melting, it's running down the rivers, it's ending up in the ocean. A warming globe is heating the oceans up and they expand. It's changing cloud formation and rainfall and so on. So we've disrupted these huge systems that are a part of our Earth. The end result, one of the end results of that is sea level rise. We're already seeing the starts of sea level rise probably. We think it's going to accelerate across the rest of this century. So if we think about the small variations I've been talking about in all of those different landforms and how that gives us quite different characteristics on these beaches, we know we're committed to a big change. Sea level rise of perhaps somewhere in the region of 60 centimeters by 2100. Other models predict it could be even more. That's going to radically change our coastal environments. How are our coastal environments going to respond to that? As sea level rises, the water gets deeper, waves will become more powerful. So if a coastline that has sand dunes on it at present, are they going to be more exposed to erosion in the future because of sea level rise? If you live on a coastline with eroding cliffs, perhaps somewhere on the Holderness coast or maybe parts of the sort of Norfolk coast that's already eroding, we might expect the rate of erosion to increase even more with higher sea levels. The salt marsh I've just talked to you about, which has developed over the 20th century because of the positive feedback of deposition, shallowing the water, and so more mud being deposited, will that go into some sort of reversal, maybe, if the water gets deeper with sea level rise? So all of our coastal landforms are going to respond to this driver of increasing sea level. But then there's other things going on as well. There's all of the management we're putting into the coast. How does the coast respond to that? When we put in groins, we disrupt longshore drift. We're trapping sediments in one location because that's where we want them to protect our development. But that means that sediments aren't going somewhere else. What's the impact of that? How does that set of coastal landforms respond? When we build a sea wall, it reflects the sea's energy back out to sea. But that's increasing the energy going across the beach. How does our beach respond to that? Does sediment get washed away and maybe the seawall collapses as the beach gets undermined? All sorts of knock-on effects on people and environments. So in understanding coastal landforms and how they develop, that leaves us in a much better place to understand the kind of changes we might get across the rest of this century. It leaves us in a better place, hopefully, to design coastal management approaches which are going to be able to cope with those changes and minimize the negative effects that coastal management can have on coastal landforms. So, in summary, what I've been trying to do is to use this site of Sand Bay and some of the variation that we have there in a really small area to get across the fact that the coast landforms exist in this very delicate balance of processes and coastal characteristics, the sediment supply, the geology, and so on. And that any changes or tweaks in that give us a response from the landform. The landform will change. It might erode away more quickly. It might build up more quickly. It may change the slope or other characteristics. and that we know significant coastal change is coming, and so need to use our coastal process knowledge and landform knowledge to sustainably manage coasts for the future. Now, I think it's only with a really detailed understanding of many of the aspects of the physical environment. You think of what we've covered here. We've covered meteorology, we've covered geology, we've covered bits of biology, ecology with saltmarsh plants and sand dune plants. So understanding of this whole range of different physical environments, but also the human pressures put on them, the tourism, the things that we're building in the coastal zone, like nuclear power stations and seawalls. Only by bringing together that physical environment understanding and an understanding of the human pressures are we going to be able to manage our coastlines off into the future. The good news is that geographers are very well placed to deliver this, because we have that sort of synoptic, broader thinking as a discipline. That's our USP, is to be able to bring together this whole range of knowledge and processes and understanding to be able to come up with solutions and to better manage our environment going forwards. Okay, so that's it for what I was going to cover. There's my contact details there if you want to sort of follow up with any questions or to reach out to me via Twitter. I've also got other GA type talks on a YouTube channel that I'm very happy to share and so on. But if there are any questions now, I'd be more than happy to try to answer them.
Thank you, Chris. That was really interesting. It's especially interesting for me as well, because I am from the North Norfolk coast, and so to understand exactly what's going on and all the different processes that are affecting it it's really quite fascinating, especially when you can actually see things changing even throughout the year after year. It's really quite a good thing. If we just have a look at the chat there, we do have a question here, if you would like to answer that one.
I can't see that one. Can you read it out to me? Yeah,
okay. So a question from Elshan, who says, what can we do in order to keep this delicate balance of coastal processes?
Very good question. Very good question. And if you can answer it, you will make a lot of money. It's about understanding those processes, so that when we recommend management, when we look at putting in management solutions, that we bear in mind what the impact of them is going to be. And so sometimes groins will be a very good answer to a coastal management issue, in that they can trap sand, they can hold sand where we want it to preserve a railway line or to defend a town. But we've got to be aware of what the impact of that is. If the sand is staying here, it's not going somewhere else. So what do we do about that? Is there anything further along the system that we care about? It might be that it's okay for those cliffs to erode or for more flooding to happen. Or it might mean that we need other management to support that coastline, perhaps beach nourishment or other sorts of approaches. But if we're taking the coastal processes and an understanding of the change into account when we put in our management, we've got a much better chance of getting things right and reducing the number of negative impacts that we have further along the coast.
Okay, well, thank you for your answer to that question there. If anybody else has any questions for Chris today, feel free to drop them into the chat on YouTube. And I'll take this opportunity while we wait, just in case, to make sure that everybody knows that this lecture will be available on the GEO website to watch again after the session, alongside all of our other past events. So you can go to the top of the GEO website and select past events, and you'll be able to see all of the previous lectures we've had on all of the different subjects, from volcanoes to coastal processes, various aspects of human geography as well. And we also have a few lectures coming up more specifically on the subject of careers. So if you have a look in our tutorial section, you'll see that we've got some live Q&As with a couple of people on how they've moved forward with their career following the path of geography, and also an even broader tutorial on where geography can take you. Okay, so just give it a few more seconds and see if we've got any more questions. And to say thank you to you as well, Chris. And you can see there's a couple of thank yous in the chat as well.
No problem.
Okay, well, it looks like we don't have anything else coming through for today, but as you can see, Chris has given you his Twitter. So if you do have anything else you would like to ask him, I'm sure he'll be very happy to help.
More than happy, yes.
Okay, great. So with that, I think we'll finish up for today. Thank you, Chris, and thank you everybody for coming along, and hopefully see you all again next time for another Geo lecture.